Okay, so last week we had an introduction lecture about what is power, why we use AC for power. And one of the things that we have shown is that when the power enters the house, the first thing it sees, the first device it will meet is your watt meter. This is the device it is used to measure the power. Now we know from DC circuit that in DC circuit, in DC, the power, we know that the power is simply V times I when everything was a scalar. Okay, but now we have AC, and in AC it's different. In AC we have the voltage V of t is a function of t, has a peak value cosine omega t, and there is certain angle theta v, and you have an I of t equal to I of m cosine omega t, and there is a certain angle theta I. Okay, so we have a angle for the voltage and angle for the current. The power stays the same. We will call it P of t, as a power of time, as a function of time, is equal to V of t times I of t. Makes sense. The power in DC is V times I. The power in AC is also V times I. But here the difference, there I am multiplying scalars, numbers. So it's very simple. Here I'm multiplying two cosine functions. So what will happen here? Then I will multiply them. We have Vm cosine omega t plus theta v. This is the voltage. This is your V of t times your I of t, which is I of Im cosine omega t plus theta I. So I will multiply the magnitude together. So we will have Vm Im. Then we have these two cosine functions, cosine omega t plus theta v times cosine omega t plus theta I. Now, how we multiply this? We go back maybe to high school or first course in algebra. We know that if I multiply cosine A times cosine B, this is equal to 1/2 cosine the difference A minus B plus 1/2 cosine A plus B. So this is, if we multiply two cosine function, this is the row. So we apply the same thing here. So we'll have here 1/2 Vm Im cosine. Now we will subtract this angle from this angle, omega t plus theta v minus omega t plus theta I. So omega t will cancel. We will have theta v minus theta I plus 1/2. Now we will add omega t plus theta v plus omega t plus theta I. So this becomes 2 omega t plus theta v plus theta I. So this is the instantaneous power. And we can see here we have two components. A component that is time dependent and a component that is not time dependent, a constant. Okay, how do I know? Because here in the angle there is omega t. So as t changes, this will be changing. Okay, but here there is no t here. There is no any t here. It is theta v minus theta I. So it's a constant value. There is no any t function here in this part. So these two, or let's talk about this one. We call it the instantaneous component or the time variant component. It will have a period is equal to 1 over, or sorry, t over 2, because we have here double the frequency. We start with omega, and then here we have 2 omega. So if the period here is equal to t, the period here becomes equal to t over 2, because we know that the period is 1 over frequency. So if we double the frequency, we are reducing the period to half. Now, these two components is not really very important for us to know. I mean, we don't need to know the two components for one reason. We will come to it now. So this is all the derivation I did here. We come up with this formula. Now, there is this interesting constant part. This is the constant part here, is the interesting thing. So what we will do, we instead of going for instantaneous power, I'd like to go for the average power. And what is the average power? I will take P of t, and instead of P of t, I will have a P. I will take its average value, which is, I will take the integration 1 over t, 0 to t, then I will take the integration of this. So when you take the integration over the period, you are taking the average value of this. Now we have two components, a sinusoidal component and a constant component. So let's do this. So your P, and I will call this is the average, and P for short, is equal to 1 over t, integration from 0 to t, and then I will write down the whole thing we have. 1 half Vm Im cosine theta v minus theta I. This is one component. Then I will have another 1 half 0 to t. So 1 over t, 0 to t, 1 half Vm Im cosine 2 omega t plus theta v plus theta I. So I'm taking the average of both components. Now, this is both, the integration is with respect to t. So here there is no any t component. So I will take this out. So this becomes equal to 1 half Vm Im cosine theta v minus theta I. So I will take this outside the integration, left with 1 over t, integration from 0 to t dt, plus same thing. This is the constant part only, 1 half Vm Im 0 to t cosine 2 omega t plus theta v plus theta I dt. Okay. Now when you look here, this is a constant. Now the integration of dt is t from 0 to t. So this is equal to 1 half Vm Im cosine theta v minus theta I 1 over t, and this becomes only t. So this will cancel. So we will have this constant part. Now let me ask you a question here. If I have a sine or a cosine function, doesn't matter, and I take the integration over one period, the integration over this, what will be the value of this integration? If I have a sinusoidal and I take the integration from, this is 0 to t, what will be the integration of a sine function? Okay, excellent, Ro. It's 0. The integration of a sine function or a cosine function over one full period is 0. Why? Because here we have positive, here we have negative, and they are equal. So they will cancel each other. So this cosine, so all of this will go to 0. So we will end up having this formula. This is a very important formula. We call it the average power, and sometimes we call it the real power. And it is in what? That the P, for short, we don't need to say P average, it's known. Your P is equal to 1 half Vm, which is the peak value, times Im, the peak value of the current, cosine the difference between the theta of the voltage minus the theta of the current. So that is the formula that we use to calculate the power. Remember, back to the DC, the power is equal to V times I. The power here is 1 half Vm Im cosine theta V minus theta I. So this is a difference between this power in DC circuit and this power in AC circuit. But we will do some more modifications on this formula, as we will see in the coming slide. But let's first have a look here. So this is your P of t. So as I said, the P of t has two components, a sinusoidal component with a period equal to t over 2. So this is the component that will have 2 omega t as, or 2 omega as your frequency. And then we have the average value, which is a constant. It doesn't change, which is this one. And as I said, we take the average over any one period or two period. Then this sinusoidal component will be cancelled, and we are left with the average value. And this average value is the one that we measure at our homes, by the way. So when we said the energy in our house as kilowatt hour, which is here kilowatt, which is the power. Kilowatt is the power times hour, which is the time. Okay, so this kilowatt hour is exactly using this formula. So your watt meter actually is measuring the power consumption at your house using this formula, or a very close formula, because we'll do a little bit of modification for this one as we move on. But before that, let's have a very straightforward example. It says here, calculate the instantaneous power and the average power absorbed by a passive. Passive means either it's a combination of resistive, inductive, and or capacitive. So we have here the voltage. This is the peak value of the voltage. So this is your Vm, and this is your theta V. This is your Im, and this is your theta I. So we want to find the instantaneous power, P of t, is equal to V of t plus times I of t. Now we know that we can find immediately the formula, but here there is one thing. I need to do something in this before we multiply them. Can someone notice or give us a hint what we should do in this waveforms before we do anything? There is something here. Okay, excellent, 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 excellent. We have to change the sign into cosine. Remember, the formula we started is 2 cosine function. So I cannot keep this as it is. So I have to change the current, and we know how to deal with that. The current I of t is equal to 15 cosine 10t plus 60 minus 90. So this becomes 15 cosine 10t minus 30. Now we are set. So if you want to find the average power, P average is equal to 1 half Vm Im cosine theta V minus theta I, which is equal to 1 half Vm is 80, Im is 15, cosine theta V, which is 20, minus theta I is 30. So it is minus 30. So if you multiply this, you'll get this is equal to 385.7 watt. So this is your average power. If you want to find the alternating or the instantaneous component, P of t, then it is equal to, again, 1 half Vm Im cosine 2 omega t plus theta V plus theta I. So it's equal to, again, 1 half 80 times 15 times cosine, then this will becomes equal to 20t theta V, which is 20, theta I minus 30, so it becomes minus 10, and this is equal to 600. Now, in power system, we don't deal with this at all. We don't use it because it's alternating and its average value is 0, so it's useless actually. So this power, or this time changing component, we just ignore it. We don't even use it at all. You will not see it. Just you need to be aware of. But what is the most important one is this. This is the power that is very important for us. This is the power that you pay the money for. This one has no value. This is just something that average to 0, so has no value. But this is the real deal. This is the one that is really we are charged for. Okay, one last point before we go. effective or RMS value. So far in this course, everything we dealt with the peak value. In AC system, we dealt always with peak value. We have a cosine function, we have the magnitude of the cosine function, and the formula that we just derived is again based on peak value. However, in power calculation, we don't use the peak value. Meaning, the 110 volt in your house, that's not the peak value of the sinusoidal. This is another value. Okay, what is this value and what does it mean? We call this a effective value or RMS value. In simple, what is it? If I have an AC circuit and a DC circuit, okay, and if I this is alternating, this is constant, okay. So if I want to find what is the constant component from my sinusoidal that will give me the same power I will get from a DC current, that is the effective value. Because as I said, this is a sinusoid going up and down, up and down. So the effective, or what we call the RMS, or stands for root mean square. The root mean square value, or the effective value, is what is the equivalent from this sinusoidal, that if I have it in the circuit, it will give me the same power that will have the DC current. Okay, so we want to map the effect of the AC to the DC so that both will have the same effect on my circuit. Without going into details, we don't need to go too much into the math. This is the root mean square. This is the formula, or the I effective. It's a root, so it's an average, so it's 1 over t, 0 to t. When you take an average value, you integrate from 0 to t and you divide by 1 over t. So this is the root mean. Sorry, this is the root. This is a square root. The mean is the average, 1 over t from 0 to t, square I square dt, which is your RMS. So your RMS will take the peak value and we apply this formula, and this will give me the effective value of the current. Okay. Now, so when we say in your house, your voltage is 110 volt, this is not the peak value. This is the RMS value in your house. The question is, so what is the relation? I don't want to derive this. Okay, what is the relation between the RMS and the peak value? So if we have an I of t with Im cosine omega t, your RMS is nothing but the peak divided by root 2. And you can prove this here if you just take this one here and you have here as Im cosine omega t, and you square this and you take the integration and take the average, you will find that this is the value. We don't need to derive this. You just need to know that the RMS value is nothing but the peak value divided by root 2. That's all you need to know. Okay, now this will have an impact on our formula. Remember, our P is equal to 1/2 Vm Im cosine theta v minus theta I. So this is the formula. Now, if I wanna, now of course, if IRMS is equal to this, same thing, the VRMS is equal to, again, Vm divided by root 2. So I can substitute with the RMS value. So we'll have here 1/2 Vm is equal to root 2 times VRMS. This is your Vm. Your Im, same thing, root 2 times I RMS cosine theta v minus theta I. Okay, now this will cancel and we will have the formula that we use for power. This is the formula that we use for power, not the big value. P is equal to, there is no 1/2. And here this RMS value, remember in DC, P is equal to V times I. There is no half. Same thing here, there is no half. There is only the cosine function. And we will see that we will end up having the same as this formula in certain conditions. I will come to that in the coming slide. But this is the formula that we use in power. And I will mention in the questions to avoid any confusion that the values of the voltage, the values of the current are in RMS, so that there will be no confusion. So when it comes to power calculations, we don't use the peak value, but we use the RMS value in all of our calculations. Now let's have special cases. So let's write the formula here. P is equal to VRMS, IRMS, cosine theta V minus theta I. Let's go back to our AC analysis. If we have a resistance R, we said that the voltage and the current will be in phase. Remember, if this is your I of t, and this is your V of t, and we know that V of t is equal to R I of t. So if V of t has an angle of theta V, I of t will have the same because this is just a constant. Okay, so theta V equal to theta I in resistive circuit. We mentioned that in the previous set of notes. So this becomes VRMS IRMS cosine theta V minus theta V, same angle, which is cosine 0, so this becomes 1. So the power for a pure resistance is equal to VRMS IRMS, which is the DC value. So we came back now from all this 1/2 Vm Im cosine theta V minus theta I. If I have a pure resistance, I will have this nice formula. So across, only across the resistance. So if I have a resistance, the voltage across it and the current that goes through it, if you just multiply them without any angle, you get your power absorbed by the resistance. So which is can be also equal to I RMS square times R, or V RMS square divided by R. All the DC formulas, we can use them. And remember, these are all numbers. There is no angle. P itself is a scalar, is not a vector. So the value of the P, it has to be a number. Regardless what formula you are using, it has to be a number. Now, if we have an inductor or a capacitor, we have seen also in AC analysis back to there that there is a phase shift or either plus or minus 90 between the two. So your P of an inductor or a capacitor will equal to VRMS IRMS times cosine theta V minus theta I. And we know that this becomes either plus or minus 90. And we know that this is equal to 0. So the power, the average power, the real power absorbed by the inductor or by the capacitor is equal to 0. Meaning that the inductor and the capacitor, they do not absorb real power. If they don't absorb real power, what they absorb? They absorb a different form of power that we don't cover in this course. Okay, so there is something called reactive power, but we don't talk about it here. This is more of people are interested in electrical engineering, so we don't need to talk about this. What you need to know is the power that comes to your house, the power that you pay money for. That is the only thing that you are interested with, which is the power. So it means the following: the loads at our home that will consume the real power, any load has a resistance. And we have seen in the previous, in the last note, that the loads are composed to two main types: either pure resistance, which is a heater type, like a dryer, like for example toaster, water heater. Those are pure resistance, so this will consume pure real power. Or a resistance and an inductor. The resistance part will consume real power. The inductor will consume a different form of power, which is we don't really interested. And this is why, generally speaking, you will see that the heating part of load consume more power than the inductive type of load, because those inductive type of load, they will consume two different types of power: inductive power and the real power that we are paid for. We don't pay for the reactive power. Someone else pay. It's not our problem as a user. The utility, they have their own way of calculating this, and it's not our business. Okay, excellent. So just two more examples and we are done with our today's lecture. Oh, this is not supposed to We're not supposed to see this, but this is very straightforward example. An RMS current I equal to this. This is your I, and this is your Z. Okay, we need to find the average power delivered to the load. So we have basically a load and a current coming here. The current is 10 angle of 30, and the load is 20 angle of minus 22. Okay, so we need to find first the voltage V. V is Ohm's law, I times Z. So I, we multiply the magnitude, 10 times 20 is 200. And then we add the angle, 30 minus 22 is 8. So it means here that the I, and these are RMS values. So the I will have a 10 angle of 30. So this is the I RMS, and this is the theta I. And the V is equal to 200 angle of 8. So this is your V RMS, and this is your theta V. So now we are ready to apply this formula directly. The average power is VRMS IRMS, which is 200 times 10 cosine theta V minus theta I. Theta V is equal to 8. Theta I is equal to 30. So 8 minus 30. So now you will see here one thing interesting. For cosine function, cosine of 8 minus 30 is equal to cosine 30 minus 8. Keep this in mind. Both are positive. So always the real power is positive. It will never be negative. Okay? So if it never be negative, this is something very, very interesting and very important to know how we can distinguish between this and this, because there is a slight difference when theta v equal to this or theta v is equal to it, although the number will be the same, but there will be a slight difference. We'll talk about it on tomorrow's lecture. Okay, so let's see here this question. We have a generator supplying power to the house through a cable. So this is a generator connecting by a cable to your house. Now this cable will have an impedance, and the house itself has its own impedance. So we have here generator supplies a house load through a feeder. A feeder means cable, same thing. So this cable is called a feeder. This is a terminology we use in power. Whose impedance, so this feeder has an impedance was 1 plus J2. This is the Z. As you can see here, the plus sign means that this is like a resistance in series with an inductor. This is what exactly it is, because this is plus j omega L and this is R. You will never see the minus here, never. It is always R plus j omega L. It's always inductive. All the cables, they will have an inductive impedance. The load impedance, this is the load impedance, is also inductive. We said that the loads is basically resistors in parallel with inductive loads. So it's R in parallel with RL. So equivalent impedance of this will be an inductive. Okay, so it's 8 plus J6. So this has an impedance equal to 8 plus J6. Now we converted the power problem into a circuit problem. Now it becomes very straightforward. I have a voltage source here, okay, and we have two in series inductive resistors in series with an inductor called inductive load, another inductive load. That's it. One loop. And in power calculations, once you understand this conversion between the power circuit or the terminology and the circuit, it becomes just a single loop. Very straightforward, very simple. Now, we are given here the RMS voltage. Now, once we deal with RMS voltage or a current in any part of the circuit, then the rest of the circuit, everything will be RMS value. So the voltage here is 120 angle of 0. And here I'd like to say something very important. If I don't give you the angle, always assume it's 0. So that is the reference. So 120 angle of 0. So we know this is your voltage. This is the V. This is the RMS, and this is the angle. Find the average power supplied by the generator. So we need how much power is supplied by whom? By this generator. We don't know anything. What is the power supplied by the generator? P is equal to V of the generator, I of the generator, cosine theta V minus theta I. Now, because we have a combination of R and L, it has to be this formula. If we have everything is R only, we don't have any L, then this will become equal to 1. So it becomes Vg times Ig. So I don't know Vg, I don't know Ig, I don't know nothing at all about this question. Okay, but it's very straightforward. Let's see how we'll do this. So the first thing, let's write down everything we know here. This is 1 plus J2. This is the impedance here is equal to, let me just go back here. It is equal to 8 plus J6. And I know the voltage here, which is equal to 120 angle of 0. So what I can find this I. Ohm's law. I know the impedance and I know the voltage. So your I is equal to 120 angle of 0 divided by 8 plus J6. Now we go back to our AC principle. So we have a power question converted into a circuit, okay? And now let's apply the circuit rule. If I divide a polar with a rectangular, I have to divide everything or convert everything into polar. So this 120 angle of 0 divided by 8 plus J6. This, if you use the software I showed to you, this becomes 10 angle of 36.9. So we divide the magnitude, so it becomes 12, and we subtract the angle minus 36.9. So this is the current. So what is the current that is supplied by the generator? What do you think, guys? What is the current that we supply from the generator? If the I that reaches the load is equal to this, what is the current that is supplied by the generator? What do you think? Same, exactly the same, because we have a series circuit. So this I, so this is actually IG, the I that comes from the generator is the same as 12 angle of minus 36.9. Excellent. So I know the current, I need to know the voltage. What is this voltage? This is the voltage generator. What I can do? KVL, simple KVL, one loop. So apply KVL. So what we have here, we have I, which is we know 12 angle of minus 36.9 times this Z of the feeder, 1 plus J2, plus the same current, 12 angle of minus 36.9 times 8 plus J6. So this is the voltage across this. This is the voltage across the load minus or equal to VG. One unknown. So we just need to do the calculations of this. So this is equal to, if we do all the calculations, addition again, that is now become an AC analysis. So this is 144.7 angle of 4.7. Now, when we started, we said that the voltage here is RMS. So this will be also an RMS. Since one quantity is an RMS, then everything is an RMS. So the power that is coming from the supply is equal to V, magnitude of V, 144.7 times I, which is 12, cosine theta V, which is 4.7, minus theta I, minus 36.9, and this is equal to 120,1298 watt. This is how much power supplied from here. This is how much power we supplied from the source. Okay. If I want to find what is the power supplied by the or consumed by the load, okay, so the power by the load, okay, how much power by the load, same thing, we will have, so the power at the load will equal to, the voltage is 120, because the voltage now across the load, not this voltage, the voltage across the load, times the current, which is 12, cosine theta v is 0 minus 36.9. 6.9. So let me do the calculation for this and see how much power is consumed by the load. I use my calculator here. I didn't do the calculations before that. So we have here 120 times 12 times cosine 6.9. So this is equal to the amount of power here, 1151 watt. So I produce 1298 watt, and the power that I consumed here at the load is 1151 watt. The question is, where is the difference went? What do you think? I I produce 1298, but I only consumed 1151. And remember, in power, whatever I produce, I will have to consume. In power, generally speaking, if I uh, produce 1298 watt, I have to consume this. So I'm consuming less. So where is this difference went? What do you think, guys? Exactly. This is loss in the feeder. Okay, this is very important, and that is summarize everything in power engineering, by the way. Okay, this is when you produce power, let's say at Niagara Falls, and you transfer this power from Niagara Falls to your houses. You transfer them through wires, through feeders. Not every single power that you produce at Niagara Falls will reach you. Part of it will be what? Will be lost as loss. Loss where? Loss in the feeder. Our objective is try to minimize this loss. We cannot completely eliminate the loss, but we can try our best to reduce this loss, and we'll talk about in tomorrow's lecture, which is our last lecture, one way to reduce this loss. Okay, so with this we are done with our lecture today. We are left with one just lecture. We'll do it tomorrow.